Hi students, in this video we are going to see the refraction of light. Refraction is the change of direction of light when it passes from one optically transparent medium to another. For example, we have air and another transparent medium, water. The light coming from air to water. It should go like this, but as you see, it changed its direction. So we call this change of direction of light as refraction. In daily life, you see, for example, a pen in a glass full of water. You see that this is the pen, but inside the water, it seems like this. You see it in another location. That's why the light coming from water to your eyes is refracted, change the direction. So you see the image as if it is somewhere else. For example, here we have a transparent medium which we call the prism. The light coming here, it should go like this, but it is refracted, change direction from air to glass. Again, when it passes from glass to air, it should go like this, but change the direction, refracted, and go like this. Now here we have some terminology. This is the incident ray, the coming ray. The angle between the incident ray and the normal. The normal is again the perpendicular line to the boundary between air and water. The angle between the incident ray and the normal is called I, the angle of incidence. It is refracted like this. The angle between the refracted ray and the normal is called angle of refraction, which we use the symbol R. So here you see that the angle of incidence is bigger than the angle of refraction. It may also be smaller than the angle of refraction, but in the refraction, the incoming ray is never equal to the angle of refraction. We may ask a question why the light refracts. This change of direction is caused by the change of speed of light in different mediums. For example, when light travels from air to water, it slows down. The speed of light in air is bigger than the speed of light in water. So as it slows down, it changes its direction. So don't forget, the change of speed causes the change of direction. What affects the amount of bending? One, the change in speed. If a substance causes the light speed up or slow down more, that means that it will refract more. We have a term here, the index of refraction. The index of refraction of any medium is equal to the speed of light in vacuum or air over the speed of light in that medium. The speed of light in vacuum is a constant which is equal to 3 times 10 to 8 meter per second. So if you have the speed of light in that medium, then you can find the index of refraction value of that medium. This value determines the refraction rate of that medium. The more it is, there is more refraction. The refraction index is inversely proportional to the speed of light in that medium. If the index of refraction of any medium is bigger, that means that the speed of light at that medium is smaller. and you can use this ratio to find the speed of light. The index of refraction value of a material is a number that indicates the number of times slower that a light wave would be in that material than it is in a vacuum. A vacuum, or the index of refraction of air, is taken as equal, and it is equal to 1. So you see that it has a refractive index 1. The speed of light at that medium is equal to 3 times 10 to 8 meters per second. For example, the refractive index of water is 1.33. It is more. So you see that the light is slower in water. It is 2.26 times 10 to 8 meters per second. For example, diamond, it is 2.4, which is 2.4 times the refractive index of air. So the speed of light is smaller in diamond. So don't forget this ratio. The ratio of refractive indexes is inversely proportional to the ratio of velocity of speed in that medium. Also in this part, be careful about the third column. As the refractive index increases, the amount of refraction increases too. For example, let's say it is coming from air to water with an angle of 20 degrees centigrade. It will bend towards the normal with an angle of refraction 14.9. But if you increase this medium, for example, to diamond is more dense than water, so the same light with an angle of incidence 20 degrees centigrade will bend more with making the angle of refraction 8.2 degrees. So as the difference between the index of refraction of the mediums increases, the refraction is more. The second property, the angle of incident ray. If the light is entering the substance at a greater angle, then the amount of refraction will also be more noticeable. That means that if you increase the angle of incidence, then the angle of refraction will be more. So if you decrease the angle of incidence, then the refraction will be less. Look at this example. The light is coming perpendicular to the boundary of the mediums. That means that the angle of incidence is 0. So here there will be no refraction because there is no angle. So the angle of refraction also should be 0. But that doesn't mean that the light will not slow down. The light will still be slowed down, but it just won't refract, won't change the direction. For example, let's say this is N1, this is N2. N1 is bigger than N2, so the speed of light in that medium will be smaller than the speed of light in the second medium. There will be no refraction because there is no angle of incidence. Now let's see the law of refraction. The first law is, if light enters any substance with a higher refractive index, it slows down and the light bends towards the normal line. Let's say this is N1, this is N2. If N1 is smaller than N2, then the light will bend toward the normal line. So the angle of incidence will be bigger than the angle of refraction. The second law, if the light travels into a substance or medium with a lower refractive index, then it will bend away from the normal line. This is the angle of incidence. The light coming from, let's say, N1 to N2, and N1 is bigger than N2. So you see it bends getting away from the normal line. So this is my angle of refraction. So the angle of incidence will be smaller than the angle of refraction. 3. The incident ray, the refracted ray, and the normal. They should all lie in the same plane. 4. The incident ray coming from one medium to the boundary of another medium is refracted with a rule derived from a physician Snellius. That's why we call this Snell's law. He found that there is a constant relation between the angle of incident ray and the angle of refracted ray. This is our Snell's law. What does it say? This is the medium 1 with a refractive index N1, and at that medium the angle of incidence is theta I. This is the coming medium N2, and this is the angle of refraction theta R. So N1 times the sine of incident ray should be equal to N2 times the sine of refracted ray. So by using this, we can find the refractive indexes of the mediums. Again, don't forget this relationship. The inductive reflexes are inversely proportional to the speed of light in that medium. Let's apply the Snell's law. The ray coming from an X with an angle of 37 degrees centigrade, so an X times the sine of the incident angle should be equal to ny times the sine of angle of refraction, ny times the sine 53. You don't have to know these sine values, it is given here. So nx times 0.6 is equal to ny times 0.8. So nx over ny is equal to 0.8 over 0.6. So in simplest form, it is equal to 4 over 3. Now I'm going to point out some important aspects. One, when we give the refractive index of medium, you should understand that it is the relative refractive index of that medium. For example, the refractive index of water is, in fact, it is the refractive index of water relative to the vacuum or air. As this is equal to 1, the refractive index will be calculated like this. In general, if the density of the medium increases, then the refractive index of that medium also increases, but they are not the same property. But you can say that if the density of one medium is bigger than the density of the second one, more probably the refractive index of that medium is bigger than the refractive index of the second one, because density is the ratio of mass over volume, but refractive index is the comparison of how the transparent medium slows down the speed of light. The velocity of the light in a medium is inversely proportional to the refractive index of that medium. So if N1 is bigger than N2, then we know that the speed of light at that medium is smaller than the speed of light of the second medium. We have the ratio N1 over N2 is equal to V2 over V1. If the light comes perpendicular to the boundary, this is our boundary, let's say N1, N2, and the light is coming perpendicular of the boundary, it doesn't change its direction because it is on the normal line of the system, but the velocity of the light changes. Since the density of the medium changes, there will be no refraction. But if n1 is bigger than n2, we can say that speed of light is smaller than the speed of light of the second medium. Refractive index of the medium is also depends on the color of incoming light. This is important. For example, the refractive index of the medium for violet is greater than the refractive index of the medium for other colors. You see, we have the white light and it is refracted like this, so dispersed to colors. The dispersion of colors is because the refraction occurs differently for different colors. So it should be go like this, the red band with an angle of this and the purple band with an angle of this. So you see that the purple refracts more. So you can see from red to purple the refraction increases. So purple refracts more than blue, blue refracts more than green, green refracts more than yellow, and so on. The angle of refraction of the light coming from the medium having smaller refractive index is smaller than the angle of incident ray. So in the first diagram, the light coming from a less dense medium to a more dense medium, so the angle of incidence is more than the angle of refraction. In the second one, the light is coming from more dense medium to a less dense medium, so it refracts away from the angle, so the angle of incidence is less than the angle of refraction. Let's do an example. The refraction of light through the mediums x, y, and z is given, so we're going to compare their index of refractions. Now let's look at light coming from x to y. It should go like this, but it bends away from the normal, so the refractive index x is bigger than y. Now let's come to y. It should refract it like this, but it gets away from the normal, so ny is also bigger than nz. In this example in page 7, we have two cases. In both of the cases, the angle of incidence is equal to 30 degrees. In case A, the light is coming from air to water. In case B, it is coming from air to glass. The comparison of index of refractions and air is smaller than n water. It is smaller than n glass. The difference of index of refractions in case A and in case B, when we compare them from this relation, the difference in B is bigger than the difference in A. As the difference is more than the refraction is more, there will be more refraction here. So light coming this way will be bent more, making this angle bigger than the angle phi in case A. With the speed of light in the medium, which has an index of refraction 2.4, so index of refraction is equal to speed of light in air over the speed of light in that medium. So 2.4 is equal to 3 times 10 to 8 meter per second over the speed of light in the medium. So the speed of light in the medium is equal to 3 times 10 to 8 over 2.4 meter per second. A light ray is refracted in the given mediums as in the figure, so we are going to compare the index of refractions and the speed of light in the given mediums. Now let's look from x to y. The angle of incidence is 50 and angle of refraction is 40. So you see that the light is bent toward the normal, so the refractive index of x is smaller than y. Now let's look from y to z. These lines are parallel, so this angle is again 40 degrees centigrade. So it should go like this, but bent away from the normal. So the light coming from a more dense medium to less dense medium. So y is bigger than z. When we make a comparison between x and z, here the light bends 10 degrees centigrade closer to the normal, and here light gets away 20 degrees centigrade away from the normal. So there is more bending here. So that means that y is more bigger than z. So when we put them in order, y is bigger than x is bigger than z. This is the answer of A. As the speed of light is inversely proportional to the refractive indexes, then the speed of light at y is smallest, then x, then z.